I'm back. All right, guys, we talked about minerals yesterday. We're in the rocks and minerals topic. It's topic 11 in your book. Okay, you'll be getting questions on it shortly, and this is your review. Just a little bit more about minerals as in a way of review. What makes up minerals? Elements make up minerals. What are elements? Those guys on the periodic table of elements. They're a chemistry thing. We're not going to talk about those other than the fact that they make up minerals. So these guys actually make up the soup of the earth. What do we call the soup of the earth? We call it magma. Actually, if it's below the surface, we call it magma. If it's rolling on the surface, we call it lava. Red hot stuff, either way you look at it, okay? And once it hardens, which means it cools, well, it has this stuff in it. It has these things in it. Now, these elements make up minerals. How many? Quick review. You're supposed to know this if you're asked. If you do take this thing called the Regents exam at the end of the year, who knows? Okay, anyways, there's 8 of them. 8 elements out of those 100 elements or so that are on the periodic table. Those are really common to make up minerals. Which are the most common? Oxygen and silicon. And because oxygen and silicon are most common, they make up what's called the silicate minerals. And the silicate minerals are things like biotite or things like feldspar. Quartz, we're just going to say, is a quasi-silicate mineral. It's actually an oxide, but that's okay because it does have silicon and oxygen in it. And those are the building blocks that make up minerals. We saw pure silicon yesterday. Pure silicon, not naturally occurring like silver and gold and those kind of things. Okay, it was really cool. Now here's the deal. Here's the main deal. The way the atoms of these elements get together to structure the mineral determines everything about the mineral. That's not in your reference table. You have to know that, okay? So what am I talking about? Tell me, what are you talking about? I'm talking about this. Let's take 2 common minerals. Actually, one's not so common. Right side up is much better, and we'll get it eventually. There it is, okay? So this is actually the atomic structure of carbon atoms making diamond. This is the atomic structure of carbon atoms making graphite. Those are in a matrix. A diamond is super, super hard. But if you put a diamond in a vise, or you stomp on it or throw a rock on it, it's going to crush. It's going to turn into a million different pieces. Its hardness is based on its ability to scratch another material, another mineral. It's the hardest mineral on Mohs hardness scale because it can scratch any other mineral. Really cool how they use diamond tips. It's actually called Bork diamond when it's garbage. They'll use it on saw blades. They'll use it at the end of drill tips because it can be used to cut through glass quite easily. If you've ever seen that at a glass factory, it's really awesome. They can just make a circle, pop it out. Very, very cool stuff with diamond. However, it's going to crush and fall into a bunch of pieces if you hit it with a hammer. You hit biotite or graphite with a hammer, this is graphite, and it might crush up, but you can also wipe up layers of graphite because of the way the atoms go together. So because of the way the atoms go together, it makes this one of the softest minerals on the planet. We use it in pencils. We call it pencil lead, not really lead, it's really graphite. A lot of people actually know that. These are diamonds. You're not going to use diamond tip pencils. You're going to go through a lot of paper. Okay, we're not going to do that. Completely behave differently, different hardness, different lusters, different cleavage, different streak, different stuff that's on page 16 of your reference table. And all I'm going to do is show you this and say, and there's a whole bunch of characteristics, but the bottom line is, why do all these minerals have different characteristics? Why are some metallic? Why are some non-metallic? Why are some soft? Why are some hard? Why do some have cleavage? Why do some not have cleavage? Why do they have special characteristics? How come they have a definite chemical composition? Why are they different names? Because of the different elements and the atomic structure of elements that makes them up. The way the atoms go together decides the different properties of the minerals. Now, those minerals, elements make up minerals. Minerals make up rocks. And not all rocks are created equal. We're going to go to the official rock page right now, which is actually page 6 of your reference table. And you have this thing called the Wheel of Rock. And what we're going to focus on, I said that all those elements are all in the soup of the earth. Elements make up minerals. That means all the minerals are in the soup of the earth. And the soup of the earth is magma. Now, magma is really hot. But if magma starts to come up to the surface, it starts to cool down. If it comes out to the surface and makes its exit, it cools down really fast. So how fast it's cooling is a really important thing. And what elements and minerals are in the magma is a really important thing. Two main important things with magma is how quickly it cools and what kind of magma it is, because not all magmas are the same. Some magmas are made out of, well, we'll actually get into that in a second. What's going to happen as the magma hardens? It solidifies, and it forms what type of rock? Igneous rock, and that's where we're stopping on that chart right now. So this is what we're keying in on. This is your igneous rock chart. Now guys, okay, you're waking up, eyes open on this one, because this is everything they could possibly ask you. Who's they? Those evil, sinister people in Albany. Only kidding if you're watching this, Albany people. You're not evil and sinister, but you know, sometimes we portray you as such. Okay, so here it is. Here's a chart on igneous rocks. Now, what do you got to know from this? I said not all magma soups are created equal. So here's the deal. Some magmas are felsic. We'll talk about what that means in a second. And some magmas are mafic. And some magmas are combinations thereof. So here's the situation. These are all mineral names. So these types of minerals, which tend to be what kind of color? Lighter, make up felsic magmas. These types of minerals, that one called pyroxene, which is green, olivine, which is green, okay, plagioclase, which is going to skew to gray, okay, biotite, which is black, amphibole, which is black. On this side of the chart, those that are darker tend to make up mafic magmas. And the different magmas form different rocks. Now, if you'll notice, two of the main rocks in our world are granite. We hear about granite countertops. Let me show you one. Okay, here's a nice piece of granite countertop. It's kind of lighter in color, and it's made up of a felsic magma, which tends to be made up of lighter colored minerals. Now, I don't have an example of a basaltic countertop, but I do have an example of a rock called basalt. Here it is, and you can see that basalt is dark. The Hawaiian Islands are actually made up mostly of basalt, and this sand right here, this sand is, as you can see, it's black. And this makes up a lot of the beaches because the basalt gets beat up by waves. That was the last unit on weather and erosion. And it ends up on the shorelines as black sand beaches because they're made up of this basalt. So it tends to be a darker rock. Now another example of that is up on the chart as well. We have this rock called pumice, which is a felsic magma rock. And we have scoria, which is a mafic magma rock. Scoria should be higher density. Look how we read the chart. You're asked on the exam, is pumice lighter in color? Yeah, there it is in the chart. Is pumice lower in density? Hello, there it is. Is pumice felsic? Right there. Also, it's made up of aluminum. Isn't aluminum a light metal? Can you imagine if we made bats, like baseball bats, out of iron? Not too many people would be able to swing around and get a hit. Of course, today we upgrade, we make them out of carbon composites and everything else like that. Okay, we also talked in the last unit about, or the last thing about silicon metal, being that it's very light. We like our cell phones to be very, very light, and they're made up of silicon materials, okay? And aluminum is also a light metal. Now let me show that. Because here I have a piece right here of, don't worry guys, hang in here it is. I have a piece of pumice, lighter color. I have a piece of scoria. And scoria is a mafic magma, and pumice is a felsic magma. And watch what pumice does. Pumice floats. It shows visibly that it's less dense. Here is scoria. Scoria sinks. Also, what's the color of scoria? It's darker, isn't it? So here's these different magmas, and they make up different rocks because they're different magmas. And they have different minerals in them because they're different magmas. So what kind of magmas are they? Well, actually, we can sort of isolate it down like this. Felsic magmas are usually associated with the main rock of granite. Mafic magmas are usually associated with basalt. Now, when we think of the continents and the ocean, well, what's higher? We can use an example like this. Okay, let's say that this is a piece of continent. Okay, or actually, we could use, let's use this instead as a continent. We can see that it's got some lighter qualities to it. And we could say that this is the ocean floor. Now, which one's higher, the continent or the ocean floor? Isn't the continent higher? The continent's higher because this is actually like a sponge. This is a lighter density. The oceanic floor is lower because it's a higher density. What's in between the ocean floor and the continents? No, not my nose. The ocean. That's what's in between them to fill the gaps. The ocean is here. This is the ocean floor. This is the continents. Continents are made up of light rocks. We actually refer to those as granitic rocks. Ocean floor is going to be basaltic rocks, which are more dense rocks. Now, to take a picture of that, actually you guys would turn to page 10 of your reference tables, but I'm going to show that to you on page 10. Sorry my back is turned to you right now, but I got to get page 10, and here it is. Here is page 10. And on page 10, in the upper right-hand corner, we have some very interesting words. We're going to shut off the lights because you need to focus in on this. Here it is. Look at this. It's talking about the density of the crust. The crust is this top black line. The crust, which is mostly made up of silicon and oxygen. Page 1, Earth Science Reference Table. And on the crust, we have a granitic continental crust. Look at that density, 2.7. And we have a basaltic oceanic crust, which is 3.0. Both made the same way. They both cool out of magma. Oceanic crust is heavier than granitic crust. And ladies and gentlemen, this is why we walk on the continents rather than the bottom of the ocean floor. Because the continents are lighter, they are higher when they first formed out of the very magma forming the foundation of the planet. Let's go back to our rock chart. So here we have our rock chart again. And once again, you're asked a question. Hey, Mr. Gratelli, granite, is it light in color or is it dark in color? Hello, we just showed it. Granite is light in color. Is granite more dense or less dense than basalt? Basalt's over here. It's less dense. Is granite made up of quartz or is it made up of pyroxene? Watch this. I'm going to section off this part of the chart because you see these names of minerals? All these names of minerals here only make up these rocks. These, or I should say it backwards, these rocks are made up of these mineral combinations. Now, what does that mean? Well, if you're a piece of granite, right here, I'm going to draw a line straight down through the granite. And if I were to draw a line straight down through, an average piece of granite would be made up of about, that's 100 down to 80, that's about 20% potassium feldspar. In fact, let me draw a line just to show you what I mean there. I'm going to draw your average piece of granite, your average piece of pumice, your average piece of rhyolite, your average piece of pegmatite. We'll talk about what a pegmatite is in a second. Here's an average piece. All right, what does an average piece have? It has these different breakpoints. It has a breakpoint here, it has a breakpoint here, it has a breakpoint here, here, and here. These are the average percentages of the minerals that cooled to make up the rock. So you got about 20% potassium feldspar in your average piece of granite or rhyolite or vesicular rhyolite or blah, blah, blah. And then you have from about 80 down to about 40, you got about 40% quartz. And then you got from 40 down to about 20. You have about 20% of whatever this is called plagioclase feldspar. And then you have about that much biotite, and you have about this much amphibole. It says that on the chart. Well, that's just an average piece. Not all magmas are totally equal. That's why when you go to get granite countertops, they don't all look the same. They look different because they have different percentages of minerals in them. You could actually still have a piece of granite or rhyolite or pegmatite that has very little pinky mineral in it, mostly white mineral in it. In fact, they're not going to call this a granite countertop. They want to suck more money out of you. So they're going to call this a quartz countertop. In essence, it's a granite countertop with a very, very high percentage of quartz, or it's been synthetically made to synthetic manufacture, not to say that the mineral is synthetic, but to make it all quartz component, which is an assemblage of many different pieces of granite. So, the percentages of minerals could be different, still making it up. If you're in the middle part right here, then you would make up, if I draw a line down, you would make up those rock names. And if I draw a line over here, you make up those rock names. So here's a question. Is there any rock on the chart that's purely one mineral? I guess you could say if the only place I could draw a line where it only goes through one mineral is right there at the end, where it only goes through the mineral olivine. And in that case, it makes a rock called dunite. And guess what color dunite's going to be? It's going to be green. Guess what density it's going to be? It's going to be high. Guess what color it's going to be? It's going to be dark green. And guess whether it's going to be mafic or felsic? It's going to be mafic. Will it contain magnesium or aluminum? Hello, it's on this side of the chart. It's going to contain magnesium, not aluminum. So what's the only difference then between a piece of olivine and a piece of dunite? Rocks aren't pure. Minerals are pure. Inorganic crystalline solids of definite chemical composition and structure. The rock is impure, so it's going to have little pieces of other things that make up that solid formation called the rock. In peridotite, sometimes you have almost pure, but most often they contain some pyroxene in it. So that would be called, in the case of dunite, it would be called a monomineralic rock, as opposed to a polymineralic having more than one mineral. Now, one more thing, and then we're done, because I'm sure you're sick of listening to me already. But hang in there. One more really important thing. I mentioned it already, how fast the magma cools also is a major player. So it's not just the type of magma, it's how fast it cools. And this totally makes sense. If you were born and you grew every single year for the rest of your life, you grew a couple inches a year, you would be quite large. You would be extremely large. You'd be Godzilla large, okay? However, if you stop growing the second after you're born, you're not very large. It's just like that with magmas. Magmas start to cool as they approach the surface of the ground. If they get caught underneath the ground and never come out, that means their cooling process, they're still going to be pretty hot. Colder than when they're in the magma chamber, but still pretty hot, so that they cool very, very, very slowly. And as they cool very, very, very slowly, all the minerals in them continue to grow, and they get to incredible size. The slower the cooling of the magma, the more opportunity for the minerals to grow. The faster the cooling, the less opportunity. In the case of a rock called obsidian, all right, guys, I want to show you. Now, this is obsidian. We call it volcanic glass, okay? Now, where does obsidian show up in the chart? Obsidian shows up over here. So it is made up of what we call and refer to as the continental magma. Remember page 10, Earth Science Reference Tables? Lighter density magma. Also referred to as granitic magma. So, in a way, obsidian is actually a form of granite. And so what's going on is we have obsidian. And we also have pegmatite. Pegmatite is a form of granitic magma as well. Only pegmatite has giant pegs of minerals. In fact, how big are the minerals? They're between 10 millimeters, which is 1 centimeter, okay, and larger. In fact, it's called very coarse because the mineral components of it have grown very large. What's the difference? This is magma that we call intrusive. This is magma that got caught in the ground, never made it to the surface, and because of that, cooled very slowly. And the slower the magma cools, as I said before, the longer it develops, the bigger the minerals will get. In the case of obsidian, this magma slop is sometimes shot out of the ground or rolling along the surface. When it's shot out of the ground, it actually can cool in seconds. We'd be able to, like, if we could imagine it, hurling through the air like, cooling in seconds, and you barely see any minerals. You do see little bursts of quartz making it to the scene, right there, a little burst of quartz. We call it snowflakes, okay, but nothing to do with snow. And this is obsidian, black glass, conchoidal fracture in its structure. They even sometimes use this stuff in the blades for surgeons because it's like glass sharp, super hard, and when they refine it, super great for cutting in cases like that. So, here's the thing. Same magma. Magma that's intrusive, magma that's extrusive. In the case of pumice and scoria again. Okay, here we go. Pumice, granitic magma. Scoria, basaltic magma. Oceanic magma, continental magma. White in color, and no minerals formed. Now we have special words for when they have holes in them like this, the air that got trapped upon that formation. Just looking for my meter stick right now. Here it is. So we call that when they have gas pockets. Let me turn off the lights for you guys. Hang in there, almost done with this. We call it vesicular. And when they don't have gas pockets, we call it non-vesicular. Anytime we can't see the minerals at all, we call it glassy. Glassy in its texture. When they're small, we call them fine. So basalt, rock called rhyolite, they're all fine crystals. Granite, and then pegmatite. Question on the exam. Which one took longer to cool, pegmatite or rhyolite? Well, you would say pegmatite. How do you know? It's got bigger minerals. The longer it cools, the bigger the minerals grow. Intrusive versus extrusive. Extrusive means it's volcanic. It came out of the ground or very close to the surface. Intrusive means non-explosive, trapped in the ground. Real quick, just to show you some intrusive plutons, and they're referred to as plutons, where magma actually gets trapped in the ground. Here's some good examples, okay, of something called a stock and a batholith. In fact, Yellowstone area is a giant batholith of magma beneath the ground. If it comes to the surface and bubbles up a little bit, it's actually called a laccolith. It cross-cuts the strata, it's called a volcanic dike. And if it layers out like the underneath of a window, it's called a sill. In fact, in New York City, they have one of the most famous exposures of that along what's called the Palisades Parkway. It is called the Palisades Sill Formation. Since the magma got trapped in the ground, what kind of crystals do you think it would have? Large or small? It would have large because it got trapped in the ground. In conclusion, this is your igneous rock chart. This side of the chart goes with all this stuff. This side of the chart goes with all this stuff. So if you have large crystals, mostly composed of pyroxene and intrusive, large crystals, mostly composed of pyroxene, large crystals would be coarse crystals. Okay, intrusive, most likely you are called, there's intrusive, you are called gabbro. I think you guys are in good shape. That's the igneous rock chart. Catch you with sedimentary next.